All right, so today's lesson is 7.6, so we're going to be learning about the cross product of two vectors. Now, the cross product is also referred to as the vector product because in this case, when we find the product of these two vectors using the cross product, instead of getting a scalar like we did with the dot product, we get another vector. Not only do we get any vector, we get a vector that is perpendicular to both of the vectors that we crossed. For example, let's say we have here vector A, and we find the cross product between A and B. We could get any vector pointed in this direction or in this direction. Okay, the lengths can be different, so there's an infinite number of vectors, but you only have two directions. Similarly, if I were to draw any vector along this screen, you can come up with two vectors that are perpendicular to all of them. One is going into the screen and one is coming out of the screen. And you can find those vectors with a cross product. Now, the equation to find the cross product for geometric vectors is A cross B equals the magnitude of A times the magnitude of B times the sine of theta instead of the cosine, which is what the dot product was. And then we need some unit vector in that direction. And because those first three values here will just give you a magnitude, and so we're going to need a direction. Now to figure out the direction, there's a way to do it. So you would take your right hand, okay, and make sort of this shape. Now, if you're doing A cross B, your index finger is going to be A, your middle finger is going to be B, and then your thumb will point in the direction of the vector that's perpendicular to both of them. So in this case, if you do A cross B, put your index finger in the direction of A, your middle finger in the direction of B, and you'll see that the cross product is up. However, if you do B cross A instead, well, now flip and do B as your index finger. So you have to do this now. You can't do this. That's cheating, right? You have to keep that shape, right? So you have to do this now. So it's actually the cross product would be a vector that's down in this case. So A cross B is not the same as B cross A. And let's show that with an example. So we have our investigation down here, and we're going to find the cross product of A cross B and for B cross A for these two vectors. So here we have A and here we have B. Now, how are we going to figure out the cross product for algebraic vectors? Well, there's a method here. So here's what we're going to write. So first, we're going to write ijk, and then repeat ijk. Remember, those are unit vectors in x, y, and z. Now, if we're doing A cross B, right, A is going to have coordinates A1, A2, A3, and B will have coordinates B1, B2, and B3. So we'll start with A, because that's the first one, and we'll write A1, A2, A3 under their corresponding unit vectors ijk. And then we'll repeat A1, A2, A3. And then we'll do the same thing for B. B1, B2, B3, repeat. B1, B2, B3. Now the cross product, this here is a lot to memorize. That's why we have this little mnemonic below. So what we're going to do for our x term, start on our unit vector in x and go diagonally, and we have A2, B3. So we'll do A2 times B3. It's that right there. And then we're going to go to the second I vector, and we're going to do a diagonal backwards, and so we'll subtract A3, B2 right there, A3, B2. So that's our x coordinate. For our y coordinate, we'll start with J, and we'll do A3, B1, and then we'll subtract A1, B3 right there. And then finally our z coordinate for K, here we have A1, B2, and A2, B1. Okay, so this can only be done with 3 dimensions, right? You can't do this with the cross product with 2 dimensions, because if you have vectors A and B, you have to go into that 3rd dimension to find a vector that's perpendicular to both of them. So we're not going to do any examples in 2D. So let's try this one. Let me just make some space here. So I'll do A cross B. So first, I'll just set up this ijk, and I'll repeat ijk. And for A, that's 2, 4, 6. So I'll write 2, 4, 6 and repeat 2, 4, 6. And for B, -1, 2, and -5. And repeat -1, 2, -5. So A cross B is going to equal, so first our x vector, so we're going to have here, so 4 times -5, it's going to give us -20, and then subtract here, so 6 times 2, so subtract 12. All right, our y vector, 6 times -1, so that's -6, and then subtract 2 times -5, so it's a double negative, so plus 10. And then finally our z coordinate, so 2 times 2, that's 4, and then subtract 4 times -1, that's a double negative, so it'll be 4 plus 4, 4 plus 4. So that gives us the vector A cross B as -32, +4, and +8. And you can do the same thing for B cross A. And I want you to pause the video here and try it. Okay, you'll have to write this row first and this row last. So these, the 2nd and 3rd row, you'll have to flip since we have the B vector first. So pause the video here and try it. And what you should get after you've tried it is 32, -4, and -8. So what this shows you is A cross B is equal to -B cross A. And we saw that in our example up above, where the difference was when we reversed them was the direction, not the length. So the length would be the same, but the direction gets reversed. All right. Let's try investigation question number 2. This one says we're going to use those same 2 vectors A and B, but we're going to add a 3rd vector C. And we're going to calculate A cross B plus C. And then A cross B and A cross C. So we're going to see if the distributive property works with a cross product. So let's go over here. And I'll write this down. A bit more room here. So we have our vector C, which is 4, 3, and -1. And we are first going to figure out what A cross B plus C is. So let me just remind you what A and B are. So A is 2, 4, and 6. And B is -1, 2, and -5. Okay, so A is 2, 4, 6. Cross, and then we need to add these vectors. So B plus C, so -1 plus 4 is 3. 2, b plus c. 2 plus 3 is 5. And negative 5 plus negative 1 is negative 6. So we need to cross these two vectors. I'll show you again how to do it. So we have I, j, k, and repeat I, j, k. You start with your first vector a, so that's 2, 4, 6, and repeat 2, 4, 6. Then your second vector, which is our b plus c, 3, 5, negative 6, 3, 5, negative 6. So this is going to equal, start with our x, so that's our I vector, 4 times negative 6, this is negative 24, subtract 6 times 5, which is 30. Then our y vector, 6 times 3, which is 18, subtract 2 times negative 6, so a double negative, so we'll be plus 12. And our z vector, which is our k, 2 times 5, which is 10, subtract 4 times 3, which is 12. All right, so when we do that, we get a vector which is equal to minus 54, 30, and negative 2. Now what we need to do is we need to figure out what A cross B is and add that to A cross C. Now A cross B we did in the first part of the investigation. We actually know what that is. It turned out to be negative 32, 4, and 8. Now what I want you to do is pause the video here, and I want you to try this method again and do A cross C. Okay, so I'm assuming you've paused the video and you've tried it. So if you did A cross C, you should have gotten minus 22, 26, and negative 10. And so when we add those, we get minus 54, 30, and negative 2. So they're the same. So the distributive property does work with our cross products. So that's a great thing to know. Last thing in our investigation is we're going to see if this is true. So A cross B, so do that one first, and then cross that vector with C, or first do B cross C, and then cross that vector with A. All right, so we're using the same vectors. So let me just go up here. If we do the first one, which is A cross B, and then cross C, again, we've already done A cross B in step 1, so we know what that is. Minus 32, 4, and 8. And then we just need to cross C, which is 4, 3, and 1. And if we do that, again, you can draw one of these to help you. After you do it over and over again, you might not need to. You might figure out your own pattern for how it works or have it visualized in your head. But you would get minus 4, minus 24, 32, minus 32, and minus 96, minus 16. Okay, and definitely draw this out and confirm that for yourself. We end up with minus 28, 0, and minus 112. Now if you do the same thing, but first you do the cross product for B and C. Okay, so you would have 2, 4, 6. And then you would cross that with whatever this equals. Your B vector cross your C vector. Okay, so you'll get 2, 4, 6. Try this cross product. So pause the video and try that. And you should get 13 minus 21 and minus 11. And then again, pause the video and try this product, this cross product. And you should get 82, 100, and minus 94. So what does this tell us? Definitely not the same. So A cross B, then cross C, does not equal A cross B cross C. So it's important to know which one you're going to cross first. Right? Follow your brackets. All right. Next thing I want to mention is we'll talk a lot more about different uses of the cross product in our next lesson. But just as a little introduction to one good use is the area of a parallelogram. So let's say we have a parallelogram here. We're in this corner. We put the tails for vector B and vector A. Now the area of a parallelogram is its base times its height. So in this case, the magnitude of A multiplied by its height. Now if we know this angle, we can do a simple trig ratio to figure out that the height is equal to the magnitude of our hypotenuse B times the sine of theta. Well, that is our cross product, or at least the magnitude of the cross product, because there's no directional vector at the end there. So it's the magnitude of our cross product, which is great, right? We can simply use a cross product to figure out the area of a parallelogram. And we'll do that in one of the examples on the back. But first, how did we come up with this long, complicated equation for Cartesian coordinates of a cross product? Now this is your textbook. This is in your textbook, so I'm not going to go over the whole thing, but I'll get you started on it if you want to try it on your own. So you start by writing the equation for geometric vectors. Then you'll square both sides. So here you have the magnitude here squared, each magnitude here squared, and the sine squared of theta. Now we're going to use a trig identity where sine squared theta plus cos squared theta equals 1, but we'll rearrange it and we'll replace sine squared theta with 1 minus cos squared theta. Okay, and then we'll distribute these magnitudes into the bracket, so we're expanding. And then you realize that right here is the square of your dot product. Okay, so we're left with A dot B squared. Now we know the magnitudes of each. We can use our extended Pythagorean theorem there. A1 squared plus A2 squared plus A3 squared, and so on. Right? Minus our dot product, which we know is A1B1 plus A2B2 plus A3B3, all squared. Now from this point, you are going to expand. And this is where I stop. This is where it gets a bit messy. But it's just algebra from this point. So you can definitely try that. Expand it all, simplify it, and what you're looking for are 3 perfect squares. So try and find 3 perfect squares that you can then factor. You'll have this one here, this one here, and this one here. Okay, now this is our magnitude equation for our cross product. Okay, so we can rewrite that as our cross product being, well, there is our x coordinate, there is our y coordinate, and there is our z coordinate. Okay, and you can also double check this. If you take this and you perform a dot product with this and either with vector A or vector B, it should equal 0. If you made a mistake and wrote this as your y or z coordinate, it's not going to be 0. A hint, notice that in our x coordinate we have neither A1 or B1. Here in our y coordinate we have neither A2 or B2. And here in our z coordinate we have neither A3 or B3. So try it yourself. If you get stuck, the full proof is in your textbook, so you can look at that. But let's move on and try some example problems. So our first example problem, move this over a bit, says if we have vector P and Q, calculate the cross product and then verify that with the dot product. All right, well, I'll do this for you one more time where I draw this out. So we'll have I, J, K, and repeat I, J, K. And then since we're doing P dot Q, we're going to start with P. So that's -1, 3, 2, -1, 3, 2. And then Q is 2, -5, and 6. Repeat 2, -5, and 6. All right, so let's figure out this cross product. So P cross Q equals, start with our x, so our I hat, 3 times 6, which is 18, subtract 2 times -5, so a double negative, so we'll end up adding 10. Next, our y coordinate, so j hat, so 2 times 2, which is 4, subtract -1 times 6, so a double negative, so +6. And lastly, our z coordinate, so k hat, I forgot my hat there. There we go. So we have a 5, subtract 6, which leaves us with the vector, here we have 28, 10, and -1. So let's verify this with the dot product. And we can choose to take this and dot it with either P or Q. I'll try dot it with P, and then you try dot it with Q. So let's do P together. So we have P cross Q, which we just figured out. And we're going to take the dot product of that with P. All right. So first we have, where's our P vector here? So multiply our x's, so -1 and 28 gives us -28. Next, 10 and 3, so +30. And next, -1 times 2, subtract 2. And that gives you 0, which it should, because if you're creating a vector with this cross product that's perpendicular to both P and Q, the dot product should equal 0. So it's a good check, but definitely pause the video and try taking the dot product of P cross Q with Q. Again, it should equal 0. That's your check. All right, let's move on to example number 2. Example number 2 says for the vectors 1, 2, 1 and 2, 4, 2, you can maybe already notice that these are collinear. Show that their vector product is 0. All right, so this is a question. Is the vector product or cross product of two collinear vectors 0? Well, let's test it. So 1, 2, 1 cross 2, 4, 2. Okay. Now I'm not going to draw this all out for you. Okay, definitely you try it. But here, so our x coordinate, so then I'm going to take 2, multiply it with 2, so I'm going to get 4, and subtract 1 and 4, so I'm subtracting 4. Then for our y coordinate, I'm going to take 1, multiply it with 2, so I get 2, and then subtract 1 and multiply it with 2, which is 2. And finally, for our z coordinate, I'm going to take 1 and multiply it by 4, which is 4. And then I'm going to take 2, multiply it by 2, so I subtract another 4. So we get 0, 0, 0, which is our 0 vector. Okay, and we can do this for any two collinear vectors. So we can take, let me go over to the side here. If we take two vectors, 1, A, B, C, and we find the cross product with KA, KB, and KC, we will end up with, let me just do this for you visually here. So our x is going to be, so our x coordinate is going to be b times kc, so bkc, and c times kb. So again, bkc. So you're subtracting those, you get 0. So let me put in that 0 there. Next one, for our y coordinate, we're going to take c, multiply it with ka, so ckA, and then I'm going to take a and multiply it with kc. So again, ckA, you're going to get 0. And if you want, you can draw it out just to confirm. Okay, but again, you'll get into the habit of doing it without always having to draw that out to help you. And lastly, for our z coordinate, right, we'll have a times kb, so akb, and then we'll have b times ka, so akb minus akb, which is again 0. So interesting, the dot product will always give you something 0 if your vectors are perpendicular, but the cross product will always give you something 0 if they're collinear. Right? Great to note, that can help us with some problems. Okay, I'm going to erase this so I have room to do our last example, example number 3, and this is the parallelogram. So we're going to determine the area of the parallelogram by the vectors p and q. And to do that, we need to find the magnitudes of their cross products. So the magnitude of p cross q. All right, to do that, let's first figure out what p cross q is. So that's the vectors -1, 5, and 6 cross 2, 3, -1. And all right, one last time, I will show you the helpful diagram here. So I, J, K, and repeat, I, J, K. So P is -1, 5, and 6. Again, -1, 5, and 6. And Q is 2, 3, -1. And once again, 2, 3, -1. So for our x coordinate, we get -5. Subtract 6 times 3. So 18. And then for our y-coordinate, we get 12. Subtract 1. And lastly, for our z-coordinate, we get -3. Subtract 10. So that'll give us, here we have -23. 12 minus 1 is 11, and -13. So to figure out the magnitude then of P cross Q, it's going to be the square root of -23 squared plus 11 squared plus -13 squared. And that is approximately equal to 28.6 square units. Now part B says determine the area of the triangle formed by these 3 points. Now a triangle is just half a parallelogram, so this is doable too. But if we have those 3 points A, B, and C, let's just draw a triangle. Let's see, we have A, B, C. First, you need to pick where you're going to draw your vectors. Remember, they should be tail to tail. So if you want, you can do AB and AC. All right, so if we're going to find the cross product of AB and AC, we first need to find those position vectors. So let me just redraw out or rewrite out what those positions are. So A is -1, 2, 1. B is -1, 0, and 0. And C is 3, -1, and 4. I just fit that in there. All right, so our AB vector then is going to be -1 subtract -1, it's just 0. 0 minus 2, so -2. And 0 minus 1, -1. Similarly, AC will be 3 minus -1, so 4. -1, -2, so -3. And 4 minus 1, so -3. So now we have our 2 vectors that we can cross. Okay, so if you need to do that diagram to help you, that's fine. Pause the video here so you can double check. And you should have gotten -9, -4, and 8. Now the area of that triangle is half the area of a parallelogram, so it's half the magnitude of AB cross AC, which is half of the square root of -9 squared plus -4 squared plus 8 squared is approximately equal to 6.34 square units. And that's it for the cross product. Tomorrow's lesson we'll do applications of both dot and cross products.